Okay, and welcome back. I'm going to talk to you about the epsilon delta proof of limits, and I drew a picture here to illustrate what's going on. Okay. Take a look at this x and y axis over here. Okay. This curve here is the function of x squared. So I wrote it over here, x squared. And the black line right here that connects this 2 to this point 4 is expressed right here. The limit of x squared is equal to 4 as x approaches 2, or the limit of x squared as x approaches 2 is equal to 4. So here the limit would be 4. You see I wrote this limit equal 4. Now as your x, so in this case here, x is this point over here and this one over here. These are your x's. Okay. Now let's look at x1 from the left. Okay, so that's why I put from the left this x1, x1. So as x1 from the left gets closer and closer to 2, which basically is your a, you approach the number 4. So here's what I did. So here's your x1. x1 is right here, okay? So I put in 1.9 because that's pretty close. If you square it, so if you put 1.9 into the function, it's going to equal to 3.61. So that means it equals this right here. You see this red dot? That shows 3.61. Okay. Now, let's say it's 1.99. Let's say you get a little bit closer, so it's right about here. Okay, 1.99. If you plug 1.99 into the function, you're going to get 3.9601. So that gets a little bit closer to the 4. Okay. So at this point here now, if you put in 1.999 and square it, you're going to get 3.996001. Well, that's going to get pretty darn close to 4. Okay, you're talking about right here. And if you get any closer, it's just going to get closer and closer and closer and closer. This right here, this interval, okay, or rather this range here, you can call it the range, the difference between this point and this point right here is called your epsilon tolerance, okay? And the distance from here to here is your delta, okay? And the same on this side. So you have epsilon tolerance here and you have epsilon tolerance here. So this range right here is your epsilon tolerance. This range down here is your delta tolerance. Okay, so this video is pretty long. This is not something that, I mean, that's why you have this over the course of a couple days in a calculus course. This is taught over the course of 2-3 days if need be. So anyway, this is your a, okay, which is equal to 2. So that you'll find up here as a generalization. And we're talking about x minus a. I'll explain this definition here in a little bit, but first I want you to kind of understand what's happening here. Why and how this definition came about. It is dependent on not just this function, but hundreds of functions, okay? That's the reason why this definition generalizes for all functions and for all epsilons and for every delta you get. So in here, let's go on the right side, coming from the right. Okay, here's x2, right? Here's a second x. Now we're coming in from this side, so we're going this direction, okay? So if you plug in 2.1, which is right about here, you get 4.41. If you come in a little bit closer, right in here somewhere, and you put in 2.01, you're going to get 4.041, which is somewhere in this vicinity. Okay. And if you put in, and if now you put in 2.001, you're going to get even closer to 4. Okay, so let me say that again. Basically, you're going closer and closer from x2, you're going this direction. Okay, so if you plug in 2.01, you're going to get 4.041, so that's going to be right around here. And as you get a little bit closer, 2.001, then 2.000001, it gets closer and closer to 4. So if you look at these numbers, basically 3.6, 3.96, 3.99, then 3.9999, then 3.9999999, you get closer and closer to 4. And if you come in from the right, you get 4.4, it's almost 4.5, then 4.04, then 4.004. And the reason why the jump is like that is because the power is squaring, so numbers rise really quick. Okay, so in this case you want to beware because usually for the most part you want, as you get closer and closer to a number, you want this little box here to get smaller and smaller. You see, I can make a smaller box if I connect this one here to that. Okay, I can make it even smaller box if I connect this. So I'll go ahead and kind of illustrate that a little bit with some color here. So what would go nice here? How about this? So I can kind of illustrate that. This right here, okay, you want basically this bounding box to get smaller and smaller, smaller and smaller, to the point where, and you can go infinitely close to it. But anyway, so now let's explain what this definition is. The limit of f of x as x approaches a is equal to L. Okay, so that's just generalizing for any function. As this x approaches this 2, or this a rather, this x approaches the a. And since you studied left-handed and right-handed limits, basically they're talking about as x from both directions get closer and closer to your a. Okay, is equal to L. Now this is an if and only if. If and only if for all epsilon. They're talking about hundreds of problems. All of them incorporate epsilon. So for all of those different epsilons that you would find in any problem, any limit problem, that has to be greater than 0. Well, obviously it's going to be greater than 0. You see? Because if you have this x over here, okay, and you are getting closer and closer to this a, well, what's going to happen is it's going to produce some type of number here. Okay, it has to be. Okay, so for whatever, if there's any distance inside of here, there's definitely going to be some distance right here. Okay, so for all epsilon greater than 0, there exists a delta greater than 0. Okay, so there has to be. So if there's even the slightest gap here, there's going to be the slightest gap inside of here. Okay, such that basically it's just saying that the absolute value of x minus a, which is basically your delta, and it doesn't matter if it's negative or positive, that's why it's saying that the absolute value, because here obviously if you're going to subtract the 2, if you're going to subtract this delta from the 2, or if you're like on the left side and you get a negative number, a negative delta, you're talking about the absolute value. In this case here, they're talking about the absolute value is going to be greater than 0. It cannot be equal to 0, otherwise you'd be on the same point. Okay, so you want this interval as small as possible. Okay, so this implies that the function minus its limit is less than the epsilon. So this range right here is your epsilon. So in a nutshell, let me just kind of reiterate what it is, what's happening here. Basically, for any epsilon, that means for any distance here, you're going to get some kind of distance here, and you want the distance down here to be as little as possible. Okay, so that way you get closer and closer to this limit. Okay, so this video is going to be a little long. It's going to be broken up into several parts, so I don't know if this is part 1. I think I might have gone over, but I'm really not concerned about that. I'm really more interested that you understand what's going on here.